All right, so what we want to do here is we actually want to start using our logical operators in mathematical expressions. So we're going to start with two values. We're going to have 37 and 23. And if you notice to the right, I've converted these into their binary values. I've separated the individual digits, and below each digit, I've put its logical equivalent. Now our values, we start all the way to the right, and if you notice, we have 1, which is true, and then here 23, we also have 1, which is true. And we're going to start going from right to left. And the first thing we're going to do is we're going to use the AND logical operator, which is right here. So here we have this row right here. Now remember, for our AND logical operator, both values must be true. So here we're going to start to the right. We have 1, which is true, 1, which is true. The AND logical equivalent to that is also true. Next we have 0 and 1. Both of them are not true, so we end up with false or 0. And we go through each digit for the numbers and we come out with a value. Here we have true and true again. We have false and false, that comes out to false. False and true comes out to false, so on and so on. So what we end up with is we end up with 37 and 23 equals 5. And the way we get that is going digit by digit to see what the expressions tell us for that logical operator. Next, we're going to look at the OR, which is this bottom one right here. So here we have 1 and 1. At least one of them is true because our OR logical operator just asks that any of the values in the expressions be true. Next, we have false and true. We look down here, at least one of the values is true, therefore we come up with the true value. And again, we go right to left and we go digit by digit. Here's a case where both the digits are false. Neither of them are true. Therefore, we come out with a logical value of false. Now, we look at the two numbers and our expression is 37 or 23 equals 55. So we take our decimal values, convert them into binary, give them their logical equivalents, and we go digit by digit from right to left, and we see if the conditions are true for our logical operators. That's how we end up using logical operators to get numeric values. Okay, here we're going to do the same thing. We're just going to use our other logical operators. We have our equivalent, our exclusive, and our implied. And so let's look at equivalent, which requires that both values be equivalent. Either both of them are false or both of them are true. So here we have on the right hand, we're using the same values, 37 and 23. We've expanded them into binary and we're going digit by digit. Both of the first two are true, therefore the equivalent equals true. They are not true for our next digit, therefore the equivalent value is 0 or false. True, and look, both of these are false. They're both equivalent. These are not equivalent because one is different. And we go down each digit. And what we end up with is 37 equivalent 23 equals negative 51. We do the same thing for the exclusive, which requires that the values be different. So here we have that they're both the same. And if we look down here in our exclusive row, we see that this is a false value. We go to the next set of digits. We have 0 and 1. These are not the same. They are exclusive. We go straight down here to our exclusive row, and we see that that value is true. And what we end up with is 37 exclusive of 23 equals 50. We do the same thing with the implied, and we end up with 37 implied 23 equals negative 33. So 37 equivalent of 23 equals negative 51. 37 exclusive of 23 equals 50. 37 implied 23 equals negative 33. Okay, what we're looking at here is the not logical operator. And simply put, what the not logical operator does is that when we take a value and convert it into binary, such as 23, all of the ones are converted to zeros and all of the zeros are converted to ones. So all of our true values are converted to false and all of our false values are converted to true. And let's see what that does to the number. The most important thing we want to keep in mind is that whenever we have a decimal value and we convert it to binary, we have a set number of significant digits. What the not operator does is that it increases the number of significant digits by 1, indicated here by the blue box, converts that to a negative value, and then it adds all of the positive values to it. So here we have our binary value, which comes out to 23. And if we go straight down, here we have a 1, it converts to a 0, another one converted to a 0. And if you notice, if you go from top to bottom, straight down each digit, they are switched. Their values are switched to the opposite value. Finally, we come here To a binary value, we add an additional significant digit. We have a binary value which is equivalent to 32, which is going to be negative, and then we add all of our positive values over there. So what we end up with is a negative 32 plus 8 gives us a value of negative 24. Let's try the same thing, only using the value 37. Here we have a decimal value of 37. We convert that to binary. Notice this is all of our significant digits. These other 4 zeros right here are actually extraneous. We don't really need them. We go down digit by digit, and we notice that we convert it to its opposite. Notice how each one becomes a 0 and each 0 becomes a 1. We get here to our last significant digit. We add an additional digit, convert it as well. So now what we have is a negative 64, and we go over, so we have negative 64 plus 16 plus 8 plus 2, and we end up with a value of negative 38. So just like any other logical operator, we convert our decimal value to a binary value, and we operate digit by digit, starting from the right, moving to the left. We see that with the not logical operator, each of our binary values are switched. We add one additional significant digit, which we make negative, and then we start adding all of the other digits to it.